We're good. Alright, so here we have the mic check. This here is the what do we call it? 4-bit switch. So basically you wait. Yeah, it is a 4-bit switch. So you put in a value. Here, let's edit it to show number. So it's a binary value, and that will then connect up this here, the 4-bit gate, to allow signals from this bus here. So say it sends it to all of them, but it only allows it through the 4-bit gate of the one we've selected. So say we've put in 3 here, 3A and 3B are allowed to go through. So this switch is one of the key components in the ALU we've made. Here it is right here. So by putting in our instruction number, say 2, which is a compare, then we can put in 2 numbers. If they're the same, we get output of 1 here, and if they're not the same, 1 and 2 for example, it doesn't work. We can also send instruction 1 what? Oh, okay. Instruction 1 here, which is our addition. Oh, these have gone weird. I'll just leave these straight for now. So 1 plus 2 is obviously 3 there. We can have a look at what's inside this. So we have converts just the 4 wires into 1. So it's just an adapter, and then it sends it through our full adders, and then we have our remainders here, and then we have carries, but we're not even using them, only in here. And inside this is the full adder, so we have say there's a 1, we'll just put out a 1. If there's a 2, the AND gate triggers XOR's there, so put there. And if we have a C and either one of these, you'll have that. It's quite nice. But it boils down to this. But here, not all of the triggers are linked up. I should probably link up. What is this? This is the it's called we'll call it address. Wait, that's not how you spell it. Yes, like that. And then this is A and B. So the address is just a 4-bit number, and this is just basically a decoder, but it's a switch. So it's a decoder, but it tells each output. It sends the inputs to the output rather than just sending a signal. So rather than just having the output of the switch, we're actually sending in data here, 2 lanes, A and B. Yeah, this is it. We can have 0A and 0B. These aren't hex, it's just lane 0 or instruction 0. But there'll be other uses for this as well. So we can just, I mean, like the full adder, you don't need nice wiring, but it looks better in the more advanced circuits for readability. I really like these decimal displays. They're a new feature. Sebastian Lag. There's a lot of laborious stuff like this. I mean, there's not much point in doing all this because I gave up on the and then this, I'll just connect this. I gave up on the decoder because it was taking too long. Because how this decoder is quite interesting. You have a signal, and I forgot about having the knots. I put them all as knots and didn't have the real signal. But what it does, when one's turned on, say they're all off, all the knots will be on, and all the real signals will be off. And then no matter which ones you turn, there'll always be 4 lit on because they're either on or off or reversed. Say you have the 1 here, it flips it, so now it's on and the opposite of on is off. So you still have the 4. And that way, using this 4 AND, which is just 4 ANDs, so they all have to be on for it to turn on. That way, each binary combination has a different output. There's not like a way of, not without code, converting it at this level rather than just manually going through. So, and even if there was, you still have to at least 10 outputs. Before I've just done up to 10, but depending on how many instructions we have, we'll need more than that. bit mask. Okay, we'll do an and. Oh, hello. Oh, hello. What do you mean by scratch? By scratch, I mean, did this not load before? By scratch, I mean we have that all of these circuits I have here are all sorry. They're all coming from a single NAND. Oh, and aside from the like adapters. So like this is a NOT gate where the input is sent to both inputs of a NAND, which just reverses it. And then AND gates, we use that NOT from there to reverse the NAND, making it just an AND again. OR gates, like this. And then using just those, we can make 1-bit registers. So here, you'd set the value and then reset it. So you can imagine when it sets, if either one of these is set, it goes to the AND, and because this is reversed, this is on, so it sends it back, making like a loop. So even when this is turned off, it still puts out, and then by resetting it, it turns off the AND gate, stopping the loop. And then we can then attach them together to make 4-bit registers. So we can set one by breaking it out here. Although this isn't quite right, because if we take a look here at the 2 is doing, wait, hold on, let's reset it. It's triggering the same ones. Oh yeah, it can store a 4-bit number actually. Yeah, 6. But if we want then like these nibbles to be in registers, we would use then something like a decoder here. Oh. So in this decoder, we have an input and it triggers a different lane basically based on the number. And we use that in the ALU. This switch here. So we have, depending on the value, it triggers a different gate, allowing the data in these lanes to go through into the ALU here to different circuits. So this is compare, so that would be 2, and then we can put in our values here, and it will send this into the compare, and because 1 is equal to 1, it's true. Said hi. Beast of true. Hello. I like and subscribe. Thank you for liking and subscribing. So yeah, that's the basic principles. I'm gonna now build a AND, which goes through each bit. I might build a counter. An AND, we can use bit masks to select a certain value, which will be useful later on with more advanced modular arithmetic. Yeah. Let's think about this. Yeah, let's see. So let's see. We want an input of 4, and then we'll 4 to 1. I'm not sure if you guys can see. So we have a 4-bit number, and then we want to break it out into its elements. We need 2 actually. Wait, and let's see. And let's check the ALU. It takes just 2 inputs, yeah, okay. And then the ALU handles sending the data. Alright, that's where's the AND? Where'd it go? Oh. Okay. I'll unstar some of these because it fills up. Alright, so we have 2 inputs and oh, what's happening now? What? Oh mate, I overwrit the ant. Shit. Shit. I called it and it, even though the case was different, it overrode it. Frick, that sucks. Okay, surely I don't have to rebuild much. Okay. 1-bit register. Ooh. I mean, this is kind of pointless. It looks fine. Mate, that's kind of sucks. It looked so nice before. No. Oh, mate, this. Okay. 1-bit register. Surely it didn't damage this. Okay. Okay, there we go. Okay. Um. Let's redo all that. So we have in 4, and then 4, split it into the separate lanes, like that. Okay. And we'll call this like what, logic and oh no, 4-bit and. So this is for the ALU. We will need ands. So if so we need the truth table for an and, but we can sort of just mentally do it. Oh, we can see what. Wait, it's just like a normal and actually. So we just need 4 of them sort of in parallel on each thing, I guess. Wait, that's so messy. Okay, we only need 4. So say the output. Nice. No. Where does this one go? Oh, when you're doing like a double stack here. These. Whoa, lots of chat. Hello, what's going on? Making a computer? Yes, I am. What's it called? What are you using? Give me a PayPal. Um, what's what called? Hello. This here I'm making is a AND for a ALU. So basically we go through each each bit and put them through an AND gate. And this will help later for any sort of modular arithmetic that we implement. This is getting it to look nice and work is very challenging. These should be on the lines. Because that makes it better. Or easier to see. Not better. Okay, so let's bring it to the back then. Because you need some frame of reference. Okay. That's nice, it lines up. Hold up. Like that. Third one. Oh yeah. Oh wait. No. That's not good. We'll need to bring this here. Because we need this one to be able to escape. Not my finest work, but it is quite a tight. You know, that's alright. Wait. What's happening in the live stream? I'm making a computer using logic gates. So 8 bits is 1 byte. So that's 1 byte or just 4 bit. I'm building a 4-bit computer. So this is 4 bits is called a nibble. There's 8 bits to a byte. So if I need like letters and stuff, to decode them, I'll need more things. So I have to use 2 registers. Because with the nibble, 4 bits, you can only have 16 possible numbers. Because you have 2, because there's 2 states, it can be on or off, to the power of how many digits, which is 4. Yeah, so we can see here, if I turn on unsigned, so you see the integer. 1 is just 1, 0, 0, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they represent numbers, but that's the ALU will be able to do this. So if I go and 1 to 4, I'll be able to. Oh. This program's called Digital Logic Sim by Sebastian Lag Lagui. I don't know how to pronounce it. Oh, out for. Okay, so it's pretty cool how like this chip, then we can go to our ALU and bring this one in here. Let's go in and we'll call this one A, and we'll call this one B. Okay, so now if we select instruction 3, we should be able to 2 and 2. Something's not right here. Instruction 3. Oh. Something's broken down. Instruction 1. 1 is got, the decoders. What has happened here? This should be triggered. All lines are powered? Oh, the AND thing is still broken. Oh, that's bad. No, wait, is that 2? No wonder everything had fallen apart, because I accidentally overwrote and oh, it took some stuff with it. Okay, so this, all this does is says, that's the good thing about packaging, because like every time you make a chip here, it packages it into like, I think it's that's how we can see, rather than having it as one big thing, like we have the 4-bit switch in here, which has the decoder. So if I put on signal 1, it's still not working. 2. Then what the heck is wrong with it? I just fixed that. The 4 and what? I just did this. Something's up here. Save. 4 and. Oh man. 4-bit decoder. 0, 1. Oh. Okay. 4-bit switch. Okay, that now it's working. Maybe we just have to reopen it. Okay, yeah, they lit up. It's turned on 3, and we can then send in 1, and 1 is 1. Oh, okay, this is good, this is good. So we can mask a bit. Oh! So this is just doing AND for every bit, which is nice. ASMR, what? Binary, 16 possibilities. What platform is it? Sorry guys, yeah, check the chat. It's called Digital Logic Sim by if you just look it up. It's on Itch here by Sebastian Lag. Or you can also play my game. Yeah. It's in development. So yeah, stick around for that. Digital Logic Sim. There is a mobile version apparently. Oh yeah, you found it is, yes. Hooray, yeah. Um, I'm not sure if it's the same version, 'cause he remade it. Probably would be. It's pretty fun, but confusing. I might end up. Well, my plan is to end up actually building this out of, but like mechanical, 'cause you can simulate the logic gates with gears, theoretically. Okay, I don't know what I'll do with this right now. But I can do like I can do a check. So see how we have these two lit up. If I light up one, it'll tell me in that spot if it's lit up. So if we light up this one, nothing's lit up there, it's not. But there, this one, that is a 1. Let's test the location value of the second digit. It's a 0. So that's pretty useful. And I can actually, I'm using up slots on the ALU, but I think I could add in like a check. So it's basically this, but if one of them's lit up, it'll be a 1. So it's like a single bit mask. Oh yeah, all good. So we can make testing values easier. Interesting. Yeah, I might as well do that. So all it will be is just a, can I copy ones? Like this same setup? No. That's a little bit sad. In 4 to 1. Okay, so here's what we'll do. We'll put in here, and then we'll use the 4 or the 4 or from before. And that way we can just do wait, is that right? We can have a single bit output. So that's interesting. If any is lit up, it will be a 1. 4-bit OR. It's the same as the 4 OR, but it's just like that. ALE. Where'd I use it? I actually don't know. Oh, mate. Oh, that's horrible. The amount. Oh. That's awful to see. The amount of work that went into this. Oh, that's devastating. Oh, that's just devastating. Oh, no. It can't be. They're like stacked as well. All the wiring, this was magnificent. No. Yeah. So they're case sensitive. I guess I'll just do it just less fancy. Oh, it was perfect, man. Why'd I have to reset the wire? Oh, that's brutal. Okay, I mean, we might as well just... Where do I even start? Because if I put it here... Oh, hoo hoo. Yo, hello. Normal gamer 4405. Tony Stark building a cave. Please explain what I'm doing. Oh, I thought what this is. What is this? What am I doing? Hold up. Yeah, this was kind of dumb because I just invented this and it doesn't. It's shit. This specific thing that I'm doing, right? Well, what I'm doing is I'm making a 4-bit computer. This here, what it did was it would take a number, a binary number, convert it into a one of these lanes, and then it would test if it's the same, right? Manually, not manually, all of them. So it was massive, and then I accidentally overwrote this and here, and then it reset all my wiring. But that wiring was kind of useless because in the ALU we can do a AND operation here on these numbers. So then I can test if this is equal to wait. Why the hell did I do all of this? You can just compare all these. Then you have lots of ands anyway. But not this many. Wait, let me think. We compare the first two. If they're the same, then we compare the second. Oh, man. No, but if they're zero, if they're both zero... Wait, is that just a NAND? Could have... Oh, man. Then... yeah, if you're ever doing something like massive with hundreds of things, there's gonna be an easier way. Could just be Okay, we need one. Oh, I remember I was looking for this before. So it's like an equals gate. It's like if they're equal, it's fine. If they're not, turn off. How do I do this? What's a XOR like? I always forget these things. Okay, XOR, that. Wait, hold up. XOR, NOR or XOR. Okay, so they're equal. They're equal. They're not equal. It's correct. It's correct. Okay. Wait, hold on. Let's view the XOR. Oh, it's made of NAND. So I made this like earlier today and I've already forgotten. Okay. Wait, this works. First try. We'll call it the equal gate. We invented this. 4-bit OR. Okay. Oh man, this is devastating. This took so long, but let's just let's get rid of this. The 16 ORs. Oh, that was just wait. No, yes, like that. 4-to-1. Equal gate. Okay, so all we have to do, it's basically gonna be the same as another chip I just built. Shame you can't duplicate them. The 4-bit AND, like this, except instead of ANDs, there'll be equals. Wait, hold up. We might be able to duplicate them. Surely you can, right? The 4-bit. Oh, what the hell is that? Oh, some, something. No, you can't. Yeah, maybe we just delete whatever the hell that is. The 4-bit. Oh, surely it doesn't like break the ALU. Come on. Oh wait, I need to fix this ALU. Oh mate. Oh wait, no, because compares the one we're working on right now. Okay. Yeah. So I just need to rebuild that. So I should only need 4 of these, 4 equals. Yeah. Oh man, this is easy cheesy. Oh wait, no, you want to do it at the end here. Oh, I've become a master at this one. Oh yeah, I get this. Well, let's bring it down. Okay, so then next we'll do this and check that. And then this. Oh, look at that, it fits. There's nothing stopping us. We're going all the way there. What the frick is this? This is some higgledy piggledy. Mate, what was I thinking just seconds ago? Is this not good? Top, that there. I mean, you know, it should work. Just compact them in a little bit. It's great being on like an infinite area. What the hell is that doing? Because you can then like just move stuff easily. Though you don't want to have floating bits. Okay, look at that. Look at that. That's incredible. If we shifted that back, we could then bring that forward. Oh, I'm thinking we shift this one back. So we can then bring this one forward. And then we don't even have to add that there because it's shorter. Oh man, look at the savings. And we could go further with this. It's too tangled. Yeah, okay. That's fine. It looks weird, but it's efficient. And now we need the 4 and. It's coming back again. Not the 4-bit and. It's just the 4 and. Not the 3 and, the 4 and. The 4-bit and is just an and on each of... Wait. Ah, yes, okay. It just does an and on each bit. With the other bit. Oh man, look at this. Oh, oh, oh. Like that. But the only problem is now if we were to drag this, we get issues, do we? Wait, we don't even get issues. Oh, because we're dragging both sides of the line. Sebastian Log, you're a genius. He's out there somewhere. Wait. Man, this is coming together. Because now we have the compare and what took massive, if my calculations are correct. Wait, why is it on now? Yeah? You told me to do like this clothes everywhere.
Why didn't you just put it in there? We could wash it tomorrow, like when you hang it out during the day when it would actually dry. What are you going to do with it now?
I'll hang it up.
What?
I'll hang it up.
Don't bring any mozzies in.
I won't hang it up outside.
Well, the hangers are outside.
There's hangers inside.
No, they're not. They're both out on the back veranda.
Why are they out there?
Because I hung my jeans out there. I'll bring them in. You hang this up. I didn't
Alright.
have to put them in the freaking bathroom like in the laundry. I didn't have to like wash them. Don't leave them in a heap out here. It's crazy to wash them down there.
It's not even crazy.
No, it's not. It's the other word. Meant
What did that do? What? Why did I do that? I don't know. Okay, oh, because they're all equal. So it compares and it's the same. Look at that. Man, that is gold. I don't know if it worked before actually because oh look. Why is it? That's interesting though. It shouldn't be on when it doesn't have gate. But it is correct that these both numbers that's being fed are zeros. But turned off, but I won't. Yeah. How we do that? We might have to add another line. No, but the trigger lines are in here. We can't have it always on. This is gonna be a tricky. Oh shit! There's lots of messages. Sorry, I haven't checked. Please explain what you're doing. Oh wait, that was from before. How do you get a computer? This digital drawing. Yeah, that's true. I'll be back. Alright, I'm back. I need to explain everything. Yes. The difficult thing about explaining what I'm doing is I would need to know what I'm doing. And I kind of hardly do. Do I study computer science? I will next. I have, but not this. It's ridiculous. In like high school, we only do Python. Python is well, I mean, it uses this. It's very high level and low level. But that's the weird thing. Anyways, this here, this equal gate, it's true that these are 0, but I kind of feel like it shouldn't output a 1. Only if it was turned on, but we don't have a way, because turning it on happens in here, and it just allows it to happen. I mean, it's fine because we use a clock for the output of the ALU. But it's like we need another switch, but that would be ridiculous to have 2 of these to switch the outputs. So I don't know, like, cause these here, these should be on a bus. Let's do that. Let's put it in a bus. I mean, let's put it on a bus. Where's a bus? 4-bit bus. Okay. We join them up like that. We move them across till it's level. Is that right? I feel like there was. Oh. Like that. Why is that not straight? Oh, okay. That's weird. Because this. Oh, this could get bad though. Because that's there and that's there. And then say we're doing instruction 1. No, instruction 1. What? It should be adding 2 and 2s, not 0. Huh? What? What is it? No way, bro. It was one little mistake and it's just affected everything. Oh, that's awful. Oh, I don't even know. Can't remember how this works. So maybe it's like this. Okay, that's right. That's right. That's right. That's right. That is also right. Okay, we fixed it. So let's go back to our ALU. Arithmetic logic unit. Okay, so by setting it to add 2 and 2, we need an out. Which is obviously, oh, frick. Obviously quite dysfunctional. Because of the fact that these are not correct. So, what do we do? Well, I guess we can put it through an isolator, which kind of sucks. So I guess I'll make a 4-bit isolator. Because this is a problem with, well, I guess you'd have different problems, similar problems, but it's a main problem with in the simulator. This flashing that you see inside the ALU. Like, so we set it to 1, and because these are both powered instead of being black like this switch here is good because these gates turn it off. I mean, we could have it, to be honest, it's probably going to be easier to make another switch, or just put another switch there. Like literally chuck it at the back. I mean, if we want to be schmick, we could like remove the second input, but like, yeah, this is probably the best way. Okay, so what I've done here, we'll add an address, and then we probably still need to isolate this though, because everything will interfere. Okay, if I do it like that, I mean it could work. Wait. No, wait. I need to remake this, but oh man. This is brutal. Look at how massive it is. I need to make one of these that does the opposite. It has a bunch of inputs with a few outputs. I mean, because we are using the bus. Okay. remaking this would just be yes, remaking this would be just insane. Take way too long. So I'm gonna go here. I'm gonna go and quit the logic sim, and here is where we have our chips. So what's it called? 4-bit switch. Reverse. Okay, 16 to 4-bit switch. It's a JSON file, which makes sense. We can love JSON. So it has information about it. Bit count. Different IDs. Pin color. And then all the wires that connect up. Wow. Kind of crazy. Crazy. But now we have this new one. We should theoretically just be able to add on to the save file. Is collection is toggled open. Can we just pop that in there? Old chip names, starred list. Okay. Oh, that's me. Okay. Let's go back to itch, launch it. Let's open DIY. Oh, mate. No way. Come on, what did I change? What? What? Why would it just not? Why would it just not open? What? Do any of them? Oh man. SR flip. Oh, this was not good at all. Why? Why? Okay, do I just remove that from there? Okay, so that worked. Where's my ALU? There we go. That's really weird. Is it this, like, 2? Say, what if we just do that, right? It's in there, but there's nothing referencing it. But will it pick it up? Okay. Oh, it must be. I'm not text that. It must be that this here. Oh. I think that's the fix, because they had the same name and then it would get confused. Not that it's like detected I've been changing stuff, because that would just be mean. Okay, it was open. Damn, it rewrote it. That's forgivable. Because my programs have done the same. And this one shouldn't be changed because it didn't even know it existed. Okay, 4-bit switch 2. Open project. DIY. Theoretically, we should have... Oh, it's not. Oh. It's not there. Oh. There we go. 4-bit switching. Let's save this. And then open up 4-bit switch. Where is it? Where? Yes. Okay, we made a copy of it. That is great. That's great. Okay, now I'm gonna do something sneaky. Well, not sneaky. We just need all of these to be inputs now. Well, I mean, we only need half of them. Oh, I could just rebuild it. I mean... Wait, why am I doing all this? The problem is deeper. It's with these. Adding a switch. No. Adding a switch is what we need. I think. Because these are the deep questions you have to ask yourself. What is the morals behind it? I'll be back. Someone replied to my Instagram comment. Oh, not that comment. Some people. Oh, jeez. Wait, you thought I was a girl until I spoke. Oh, man. That's pretty funny. You're not the first person. Did you... Okay. Let me think about this. So, we need... no, we do need... I could... I mean, I could just have a gate that's triggered by another switch. Just an allow switch instead of a full switch. Yeah. I mean, 'cause these logic, yeah, fuck it. Okay. Wait, I just said yeah and then immediately forgot what I was thinking. We need we just need the decoder hooked up to gates. So I'll make a new one. Like, it'll just sit. The decoder hooked up to gates. I could just sit that here. No, I'll make a new one. Let's just. Oh no, we'll just. Okay. Let's take the 4-bit decoder. Hooked up to gates this time. We could have done that before. No, that's what I did do before. Oh, but then am I... Then am I just doing the same thing? It's literally the same thing. No, it's not, because... Ah, man, I cannot even begin to explain what I'm doing, because I have no clue. We just need 16 of these, that's all I know. 4. Yay. 8. Oh, Silverclad. Oh, damn, it's the moderator, he's back. 8. 16. Okay, we'll just kind of like sit just somewhere up here. We also need 16 inputs and then 16 outputs. Wait, oh. Hold up. Hear me out. 16 4 inputs. Yeah. Yeah, no, this could work. I think. And then we just have this gate here. We just need 16 gaps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then we'll just leave 1, so it's like there. There. Yeah, we're doing this. Yeah, look at that. Yeah, no, this is gonna be easy. I don't know if I could actually use this on the other switch. I can't even like start. I just have to not think about it. If I think about whether, because that switch is the other way, right? You have yeah, a lot of outputs, a couple inputs. This one is just gonna be a couple. Wait, no, bunch of. This one will be a bunch of inputs, couple outputs. One output, singular. Then I'll have to fix some stuff, and we're never gonna be able to get overflows to work in that case. I don't know how I'm gonna do that. For adding bigger numbers, like more than 8 bits. That's time for... I mean, I guess I'll just have to use 2-bit adders and then include the overflow in the second half of the nibble. Man, if someone didn't know what I was talking about, they'd be very confused. Like, all 7 of you guys watching are probably like, I don't know how anyone could understand this, because I sure don't. I'll try to explain. I've explained it a lot. Okay, but this and see how they're going black. That's because I never finished the decoder. Wait, what's this called? We'll call this the 16 to 1, 16 to 4 bit switch. Okay, yeah. Why don't I just finish the decoder right now? The decoder. Decoder. Okay, so what this decoder does, it turns binary into a signal. Not a signal. Oh, why are they stacked? Oh, is it because it's too zoomed in? That's stacking them? No. That would be weird. Okay, I don't know if this is too many. It's probably not. Because there's 16 outcomes. Alright. So what did we get to? 7. Number 7. If I put in number 7 here. Oh, I remembered there. But then we get 8. It's basically what this is doing. This is just turning this square into this number. But we can't get this number because that's part of the simulator. We need to get it using all of this, because when it lights up these specific things, well, that only happens when it's a number 8. I think that's a decent way of explaining it, because that's literally what it is. I hate when people say, yeah, even though I do it a lot, people say basically, when it's like, no, that's not basically, that's just completely all of it. It's as if they're like, yeah, that's the simple version. But most of the time, well, sometimes it is the simple version. Sometimes you say basically, but sometimes people just say basically. Or even when it's not basic, like it will be the most complicated shit. You know? I'm going, like when you're focusing. Is that a multiplexer? Yes, this is... No. Wait, is it? I think it's the same thing. Let me see. Wait, yes, it is a multiplexer. Wait. Wait. Let's... Because I'm it's a binary decoder. Data selector. Yeah, that's what it is. That's what it is. Wait. Ooh. Oh no, it's not quite. It's very similar to a multiplexer. It's part of a multiplexer. So what the multiplexer does, right? I forgot what it was. So it includes one of these. It takes a binary signal, right? So say like 7, and it lights up 7, but then 7 is something. So an ALU, this thing here is basically a multiplexer. It uses this switch, which is just one of these decoders, but it has these. So when you select a number, right, with a binary number, oh, I can't select it here, but then it allows the data to pass through, because in a multiplexer you've got your inputs and outputs. Oh no, sorry, inputs and the one output. So it allows the inputs to pass through into a different function here. So here we have addition, comparisons, and then has one output. This doesn't quite work just yet, but this is essentially going to be a multiplexer. Well, it is. So let's say we select add, and then what the flip? Add 1 and 2 and 2. Well, it's 4, but we can't really see it. Let's do if you were to look at the output here, you would see 4. 2 and 2 is 4. 2 and 1. 2 and 1 down here. Then we get 3. So, yeah, this is a multiplexer, and this is the key component that makes it multiplex. Where the hell? I've lost it. There's too many. This one. 9. Lights up 9. 10. What is beef? Are you good in electronic? What are you doing? Oh, a lot and not much, because I'm making a 4-bit computer. That's what I'm doing. Well, no, that's basically. Okay. Ha ha ha. 11 out of 16. Wait. Oh my goodness. What the heck is Schmecko? Which one is connected? Yeah, that one. It's weird. I mean, I've kind of gotten used to it now, but I found it weird how this 1 is down here as opposed to being up there. Maybe if we make it signed, well then 1 is still there, and then that is also weird. Signed is just includes negatives. Took me way too long to realize that. Not to realize, to actually, yeah, when I was making a game in C, because I would just use unsigned, because I knew it was less or more. Less is more. I knew it was simpler, so it would run better, smoother, maybe. No, it wouldn't really, because it's still 8 bytes, 1 bit. It was a 1-bit thing, 1-bit number, signed integer. No, 1 byte. Shit, what am I saying? 8-bit. No, yes. 8-bit signed integer, unsigned integer. Because there's signing. Oh, what have I done? I just made them all 12. Signing, like digital signing. I thought it was like something like that. Okay, I made them all. What? I made them all 0. Not even 12. That's 12. Okay, this should be lit up at 12. That shouldn't be there. It should be here. What? Should that? Oh, wait. Okay. Yeah. There. You just have to manually go through. But once I've done this, then it should all be smooth sailing, because I'll never have to do this specific laborious task again. There'll be different ones. Wait, that shouldn't be. 13. 14 out of 16. We're moving along. Where all the time? Am I streaming? Yes, I am. What to say? So what you guys been up to today? For anyone watching. Oh. Silvercloud asks. There were people talking before, but then I had to hang up the washing, and then everyone left. So that was sad. Huh. The world. It's quite interesting, really. Okay, where are we at now? He's keeping. Wait, what? Before he reads the chat again, he's keeping me in his basement. No. Oh, yes, we've done it all. We've done it. That was 15 because I forgot 0 counts as 1. Well, no, not as 1, as one of the numbers. Yeah. I could simplify this. No, I couldn't. Not without shifting them. Ay. There's the decoder. Now we just need the... Oh man, I've just lost everything. 16 to 1 bit switch. There we go. 16 to 4 bit switch, not 1 bit. That would just be silly. That's what this kind of is. 4 bit to 1. No, it's a decoder. What am I on about? Where'd all the time go? Started to fly. Oh, said hi. Huong Lan. Make a GPU. Ugh, I haven't gotten food in days. What are you on about? Make a GPU. Well, you see, a GPU is actually much simpler than a CPU because it has. Well, I mean, I said. Yeah, it's got less going on, but more going on. It has less complex functions, just heaps of them. Like a lot, really fast, but for that you need to pack heaps of stuff in, all close together, and really it would run quite not very good at all on a simulator, doing any intense processes because of course you're emulating it all through a CPU. And I guess they could write it in like CUDA. I doubt. With this program, definitely not, because it's on a Mac, and it wouldn't have been written for that. But also, because it's a 4-bit computer, if it was a GPU, that would be kind of not like you're not going to be able to do any sort of GPU activities in 4 bits. What? The hemorrhoids are acting up. What? I'm just. What hemorrhoid? Hemorrhoids. What? Is this? Call the police. What the hell do you want, Silver? Call the police. What is this guy on about? You're a moderator. You're supposed to be moderating, not doing stuff. Okay. Yeah. Oh, now we just need a bunch of inputs. That's what we need. A bunch of inputs. Like a butt ton of inputs. Too many inputs. Well, no, we need them. Okay, so what this will be doing is if there's any that are on, like, so say the equal one. Yeah. Hey. Sorry about that. Okay, let's go to our ALU. See, this one, this compares if things are equal. And if we select it, it's number 2. Well, so sorry, if we don't, if we just put these outputs onto the bus, then you would just have it on, and that wouldn't be good because we're not using it. But it is correct in that 0 is equal to 0. But we can't detect if it's off or on, so this switch here will just only allow the outputs if it's being used, if we want to use it. And that would be nice, because then I could have a working calculator in a couple days. Because this program, we can do key inputs, we can do all sorts of this. We can build a full working computer, and maybe even if I can make a Python program that ports over things into these, like memory, load stuff into RAM. We can make an emulator for like Game Boy games, Commodore 64, probably Game Boy. Wait, no, hold on. What am I saying? That would be a completely different project, because in this one I'm making my own architecture. But we could be able to, I don't know, import, make codes in machine, make programs in machine code. Don't let Intel know this guy. My computer thing can Epstein files. Wait, hold on. What are you doing? Give me a recap. Oh, okay. Wait, make it. Hold on. What are these things? Okay. Let me explain it. So basically, this here is a decoder. So we put in. Let's add it in. An input, a 4-bit input. So bit is one binary number, 1 digit basically. And we can view here. So say we put in a 1. It's going to be going, oh, this is 0. But here's 1. So on channel 1, it's going to go here and allow whatever number this is to enter, or to go through, right? It's a gate pretty much, which the gate is just made of individual gates. So we have the number here, and it splits it and does each 4. It's a transistor basically, but 4 of them all in parallel. So this will then allow it through. Like it will look like that, but obviously not go back in there. So by triggering a different number, we're allowing data to flow through there. Oh, we've got them all linked up. And now we can add in a bus, a 4-lane bus. A bus is just one line that multiple things connect to. So it's like one big wire. I mean, it's not necessarily bigger, but everything connects to it, right? So let's just quickly connect a couple of these on. Let's just demonstrate. So say, and then we can do an output like this. Okay, here, this is the demonstration. Okay, so say this one we have all, this one is like this, right? So by selecting channel 1, channel 0, we're seeing the same thing here as what's on here, right? This, by selecting channel 1, we're allowing this information to flow through the bus onto here. This thing's the bus, this long red thing. By selecting channel 1, we're allowing channel 1 here, this one, to flow through onto the output. And then channel 2, it's the same thing. We're allowing this second one, 0, 1, 2, to flow into the bus. So you notice this here is the same as the output. I'll label these to make it easier. 1, 2, 3, 4. So this is kind of like, this is a part of a multiplexer. And a multiplexer is an ALU, arithmetic logic unit, is part of a multiplexer, and it handles different computations. So here you'd be selecting like addition, subtraction, multiplication, whatever, and then the data is the numbers that you're using, and they'll go through. So let me just finish labeling this. Oh, 5, 6, 7, 8. There's 16. 9, because that's the maximum amount. You get 15 with 4 ones, and then the 0 is another one. So 4-bit CPU. Holy cow, you look good. Make a 32-bit computer. That would be insane. Like 32 bits. This is 4, and it's already like insanely. What software? Oh, sorry. Software. This is called. Not that. It's called Digital Logic Sim by Sebastian Lag. Can you see that? I don't know. Yeah, Digital Logic Sim, made by this guy. And you can. It's even on mobile. Double Dabble. I think this is similar to what I'm making. Oh wow. Someone made it in Minecraft. Double Dabble. Binary numbers into binary coded decimal notation. How did they do it with such little gates? Wait, never mind, that's not gates. Huh? Why are there so many in Minecraft? Double Dabble conditional adder. But how the heck is he? This is kind of like the binary coder. I'm not sure. Did you know that a guy in Australia is making his own? Wait, what? Really? That's interesting. Yeah, because we only have like getting distracted. Wait. Collab with them. Make 32 bytes of RAM. RAM's easy. I'll make RAM right now. Wait, hold on. I'm getting distracted. I will make RAM. let's just get rid of that. Oh, wait. 32-bit switch. Oh, there we go. This is lovely to see. Wait, in. Oh, hold on. Let's open it up first, and let's rename it from in to be more descriptive. This was the address, and we can turn that off. Okay. So we'll go back to the ALU. Oh, save that. Okay. Okay, so then same thing. The address from here. Let's bring it up so that this is in line with that. Okay. Okay. 0A0B. Like that. And then, oh, this, okay, wait, so if we do lane 1, 1 plus 2, let's chuck this into the bus. Wait, I don't even need a bus anymore. Oh, that's so wonderful. We can have a singular output once again. Something's not right. What? Oh, silly me. I connected it to the wrong line. There. 1 plus 2 is 3. Oh, we're back in the game. Stay hydrated. This guy, I should make him a mod. It's empty. He made a few 12,000 transistors. Wait, no, sorry, 1,200. Yeah, because you see, ASML, I think that's what they're called. They make, they're the only company that makes the machines to engrave the silicon wafers. So they like control the whole market. There's only like one company. All computers like basically originate through their machines. They have such a monopoly. It's outrageous. And then we got TSMC. All the companies get the chips from there. We need more like independent chip manufacturing. Like it's so expensive, but there kind of needs to be like a global reset. I'm a communist. ASML is so freaking sick. Yeah, like sick in both ways. Like it's incredible. The Sam Zaloof. Wait, is that his name? They're sick as in like the the machines are incredible. Like the engineering is insane, but they're also the billionaires that just control everything is not good. And then Sam Zaloof, let's see him. Born 1999 or 2000. He's an American electrical engineer. Chip fabrication. Whoa. Wait, electrical engineer.
You're looking at something so astonishing, it almost...
Lithography stepper. Maskless lithography. Yeah, wow. Because like this, reactive ion etching. Jeez. Damn, this is high tech. But obviously not as well. Nowhere near like what the full like industrial ASML would be producing. But who is this guy? This is insane.
Here is a tick that's been sputtered with copper.
A tick?
I'll show you the chiller in a few.
Oh. It's mad. I'll have to look into this later. But like, this guy. Hello, it's you. But lower like the thing is we've become so used to incredibly high rates of like such powerful machines. It can do billions of computations or whatever, how many gigahertz processors and all this RAM and all the storage that. What's Imarina? That software engineers, the people designing the programs, have become kind of, well, lazy, and then we're also being replaced with AI, so that these programs are not efficient enough, so that then they're so inefficient, we just then need more and more processing power, using more energy, cramming all these transistors on a chip, that if we could do what we're doing with a lot less transistors and a lot less power if things were made more efficiently. What's your computer specs? I'm on my MacBook Pro M4 right now. It's the cheapest MacBook Pro M4 with 10. Oh no, it has 1 terabyte storage. 10 core CPU, GPU, NPU as well. I think maybe that's inbuilt GPU. But I have a Linux server with a 32 gigs. LM Arena, open platform for evaluating AI through human preference. What? Oh, LM. Hello. I've never seen this. I sometimes use ChatGPT, but oh, I don't. Oh, oh, what? I don't like to use AI. What? Okay. So it just lets you use AIs. It's Chinese, right? Hello, it's nice to meet you. This is better, right? It didn't detect my language. What's your kidney, right? Oh, every AI for free. DeepSeek. Why is DeepSeek in Chinese? Please explain a multiplexer. That's kind of cool. Mox. But then you have 2 answers. Okay, I mean, it's kind of good. Oh, Philosopher X. Don't like that. Because I guess you can validate things better. Transparency and privacy, but it's probably better to access them directly than through this third party, even though they say this. It's pretty quick though. Interesting. Top left. AI is. Wait. Oh, you can. Shared publicly. Okay. Upload. Oh. Direct chat with. Oh. Whoa. That's cool. GPT-5. 120 billion. Hello. We need to no special instructions. Discrete back. Damn, that was very fast. But of course, maybe shared publicly. Not that you should ever be feeding sensitive information. Alright, let's get back to this. Because, oh, it's piggery higgery, but I like it as well. Yeah, might as well. Wait. You know what I'm thinking? If we go back to the ALU, can we not just connect this into there? No, we can't. Okay. I like this. This actually looks really cool, in my opinion. We'll just put in a 1, 2, 4. Not 1, 2, 4. 1 into 4. Out 4. It's like a. It looks like it does stuff. It does do stuff. Yeah, we have these on the 4-bit adder, but they're not really being used. We'll chuck this up here. Yeah, these carries. So with an ALU, no matter what you put in, it'll always have the same thing, because there's no memory or anything like that. Alright. 1 plus 1 is certainly 2. 1 plus 1 is 1 is equal to 1. And that's what 3 will also tell us. Oh, once I link it up. In this circumstance, but there's circumstances in which wait, is there? Hold up. Yeah, compare and are different. They're certainly different, because like that's just 0. That was just a 0. That's just a 1 there. Like, it definitely does different stuff. Compare is more like a specialized version of the AND, because if you view this is just testing both sides. But this is testing all of them. No, wait. Equal. I guess and is doing more. We'll save it as 4-bit and. Okay, let's go back to the ALU. Oh, 4-bit compare. Oh, Veritasium just made a video about EVU machines and explain them. Oh, hello. Damn. I always forget to check chat. I better get going. Goodbye. It was nice. It was nice. Make sure to subscribe. Veritasium. Let's see. I always watch Veritasium. That is true. You've been playing the game of life, right? Oh. Oh, this one. EVU machines. Yes. Oh, yes. Sorry, I didn't click. I'd started watching this. He talks about ASML as well. It was. I apparently didn't finish it. Am I retiring? No, he was not retiring. It's interesting. It's insane. But it's also too much, in my opinion. I feel like we could do the same with much less processing power if we make things more efficient. Of course, for some things, but like any process intensive thing. Oh well, AI is the main one. But we can just do without AI. To be honest, it's not good. But say like games, so many games are really inefficiently made. Like EA is a bandit for that. Just having the most clunky stuff. So if we made them more, but it's not gonna happen. But the world needs to take like a step back. In a lot of ways. The monopoly that these companies have, it doesn't make anything. There's no innovation because no one has the resources to innovate. Everything costs so much. It's just an endless cycle, but that's capitalism. Anyways, we have add, compare, and I was just talking bad about AI, but let me just ask ChatGPT again. Compare sets flags. Okay, more than or less than or equal to. Oh, that is interesting. That would make it very complex. Because right now, that is true. Because compare, all it does is test if they're the same. Which is the same, not the same, the same. But if we were to instead set flags, we could get a lot more information. So we could use it for other things, like is it more or less? How would we check if a number's more or less? Greater than. MSB. Oh. Most significant bit. Wait, someone's already built. Oh, of course. Okay, so let's think about this. The first one and the second one. No, what is this? No, it was no. What is this? Zone? Let me bring this over. Okay, so they put them into this logic gate. And then this is an AND, right? But that's interesting because for them all to be more, because you could have a number, it's not necessarily all or more. Because like if you have 1001, then you have 0110. This one here is obviously bigger, but so if we mask it, or wait, we could AND circuit it. No, never mind. What the hell is this? What would that even put? Zone. Let's test it out. So it's like a XOR gate with a knot on the end. We did something. We did something similar to this with the equal gate. Wait. We did do that. Wait, what? Wait, I didn't see these messages. So how are you today, Silver? Fair enough. What are you having for dinner? You know me very well. What? Wait, how do you know? Did he... What's going on in chat? He knew what you're having for dinner. What's happening? IDK for real 501. You're not slick, Silver. IDK for real 501. Who could that be? 501, that's an interesting number. KGB. Let's take a look at this 501. It kind of reminds me of the 501st Legion. That's interesting. And this IDK, where could that be from? Where could that be from? IDK. Okay. So this is like the equal gate. What? Alright. So all this is doing is just checking that it's equal. Wait a minute. Okay, wait, hold on, it's the same. I just had it all into one big ad. Alright, I was worried I'd done something. Stole our tech, huh? Wait. How do you even know what I ate? I'm onto you, IDK. Pin him. Who, which one? What's happening? Huong Lan? Are you one of them too? No, Huang Lan kind of reminds me of. He's a spy. No, he's not. He's a friendly guy. How the hell? How the hell can a person go to work in the morning? Wait, yeah, this is the same thing. Stall attack. Wait, or should I call you Jacob? Something's going on in the chat, guys. Something's going on. But wait. Hear me out. Hear me out. Hear me out. Where's my thing? I've lost it. Zone. Oh damn, this is okay. That's just what we made. The equal gate. It is the equal gate. What we need is a way. Okay, let's first input 4 in. So we have 2 numbers coming in, and we have 1 number coming out. Let's split 4 to 1. I've seen this before. Okay, so we've got that. We need to check the first bit, the last bit first. How would I do this? If this one and this one like or? No, because that's not conditional. He's a professional pickleball. How's your professional pickleball coach? Manas Lahan, hello. I'm making a 8-bit computer. We're trying to. Wait, could it be that NAND was the key all this time? Wait. Oh shit. I need like. Oh yeah. Wait, hold on. We can do it with 3 state buffers. It's probably not the best way, but it will work. So we have this as the enable, and this is the in. Yeah, maybe that's the word. And then for this one, we have this as the, and this is the enable. Wait. Wait, what was I thinking? I don't know. No, because that will just exclude. Then what? Olympia. No, he retired. Over 60s pickleball. What is happening in the chat? Make 32 bytes of RAM. Alright, fine, I'll do that because this is giving me the pick. Okay, so first we'll use a 1-bit, we'll use a 4-bit register. We have store and reset. I mean, we've already most of the way there. Okay. "32 bytes around." This should be schmick and clean. Store and reset. Okay, so we'll go. Woo, I like to see this. Okay. Oh, wait. I like this. Okay, so store the value 1. Wait. Oh, it's one number. Okay. Wait, did you say 32 bytes? But it's a 4-bit computer. I can't use bytes. Well, I can, but I'll use bits. Nibbles, sorry. So this is 1 nibble. We can store a number here, say number 15, store, and then we should be able to view it here. We can reset it. Okay, that's 1 bit. But now we want more of these. I can use the switch. Yeah, 4-bit switch that I made previously. Holy, it's huge. That's insane. I forgot how big it was. We probably don't need, but we certainly don't. This is like a 2-lane, but I guess we'll just use it. It's easier than make a whole new one. Okay, we're missing. I forgot. Okay, so sorry, I'm off to the side here. In our number, we want unsigned. So this is the address, right? It's already set up address. So say we register 0. Oh, I'll add in a bus. Yeah, let's do a bus. Okay. So this bus will. These will be the set and reset buses. Although, hold up, we don't want to reset all RAM. We want to be able to reset individual ones. So that's good that we have this second channel here. Oh, this is going to be huge. 4-to-1 bit. So it would have been probably better to do it in smaller chunks. No, it's fine. 4 set and reset. Okay. I will do 1, 2, 4. Yeah, I mean, okay, this has turned out well so far, because yeah, having a second switch, I could have done like 2 switches, and that would have probably made more sense to make 2 smaller switches and just put them together, but for whatever reason I didn't do that. Well, I needed more, so I just did more. Maybe one day I'll do it the other way. Yeah, it'd probably be better, because there will be circumstances in which we don't need all of them. For 16 nibble RAM. It's weird they're called nibbles, but okay. 1. So we should be able to set. Oh, I'm on the wrong one. No, I'm on the right one. Why? Just be. Ah, I always forget it starts at 0. Okay, so we set 0. What's happening now? Why isn't it setting? Oh. Because this is the value, okay. I forgot. Okay, like this. Okay, so we set in our number. Let's do unsigned. It works very similar to the ALU, this RAM. So let's set 3. Set 3. And then we can, it'll always just show this segment of RAM. Let's, this is not too good. Because every step it gets a bit behind. Surely we can, because I only have 2 instructions. Let's make it like this. So we have it in, for, in, 4 to 1, like this. Out 1, yeah, we'll do it on the first 2, because that makes more sense. Okay, so we'll do in and 4 to 2. Okay, this is a weird thing, but it's a thinner chip. And that way then we can almost, we can have it very close to being, to fitting. Because we want it to be tileable. What's going on? Wait, hold on, let me scroll up. You see Jack? Who you say? Silverclad's name is Jakub. I can give you his full name. Yes. Oliver's info. Yes. Shut up, IDK. ID number, please. Jakub Turco. Turco, I had to check. Where do he live? He's lying. What is going on in the chat? Something is up. It's probably more interesting than whatever I'm doing. Let's open. I'll save this. Okay. Let's open, customize. Surely we can. Like this space to. It looks so cool. To me, anyway. This is disgusting. Oh man. 2B. Wait, yeah, this is almost exactly the same as the ALU. Oh man, we're gonna need some. Okay, you know what? No, I mean, I don't want to include these into the chip because there'll be times, I mean, there won't be, but it feels weird to have a 4 lane for just 2, even though it would make things a little bit easier. You know what I mean? I'm sure you do. You know, I'm kind of liking this now. It's getting better. So all the B channels should be the set and reset pins. I might add like another one like flip or something. So that's why I've left it as a 4 for now. Yeah. Probably won't add in a flip, but it could be useful. Otherwise you have to do it with an ALU, which that's just like silly when you could add it. Well, I mean, you still, I don't know. I've lost so much track. Okay, this is the address. Speaking of address, can we get Turco's address? Okay. Register 1, we'll set the number 6, set. Okay. Wait, hold up. Is this working? I think it's working. Okay, register 1. Oh no. What's happened? Oh. Oh, that's probably it. We're not setting it even. I was on the wrong pins. 6. Oh my god. Why is it doing that? Wait, does this happen to have 6 as well? Oh, because it was held down. Okay, reset. 1 has 6. Oh my god. Oh my god. Han Luong. Huang Lan, sorry. Oh my god. We've had a breakthrough. We've had a breakthrough. Look. Register 1 has number 6, right? Let's go up to register 2. Let's say number 9. Number 9. Oh, sorry. Let's number 9. Set. Let's go back to register 1. Yeah, 6. Oh my god. Oh my goodness. This is incredible. We have addressable RAM. Number 2. That's still. Wait, 15. Huh? 6? Wait, I thought. Hold up. 9. I thought there'd been a leakage. 6. How about we set in 7? Okay. Okay, it's still at 9. Oh, this is incredible. We've got working RAM. Catch iguanas. Catch some dome cards. Domio cards. What's the logism? Oh, logism. Oh. Oh, logism development is indefinitely suspended. Compatible with my paid responsibilities. Never received a dime. That's actually crazy. That's deep. Free open source. That's sad as well. Poor guy. This looks quite incredible. I'll have to copyright. Hold up, he said it was open source. BSD, Mac, Linux. That's incredible. I might have to try this. Sad, yeah, it's sad. Poor guy. What's dome cards? Demo cards. Democrats. Oh, Democrats. We've got working RAM. We've heckin' done it. 7, 9. Mate, we're making it. We're making it out. We're building a CPU. Oh, hold on. Yeah, go catch Democrats. Why? What's... Don't catch the Democrats. Alright guys, we're making it. Doesn't have 2, it would be interesting if this had 2 lanes. Yeah, I should make just a 16-bit switch with 1. Though both times I've used it I've needed 2. Oh. Let's chuck that back. Oh boys. I don't want these to cross over. It wouldn't make any difference. Wait. Oh, they don't need so much distance. Mate, this is incredible. We're designing the generation of computing, the next generation. Nothing about this is remotely next gen. This is at least like 50-year-old tech. Or what they were at 50 years ago. Maybe. Oh damn, I figured that would be correct, but boy was I wrong. One, two, three, 4. Oh man, there's still a lot to go. Ooh. Like, the crazy thing to me with computers is like, you know how the CPUs, they're built for errors, because like a third of them, they just disconnect. Make a 16-bit breakthrough, eh? It's a breakthrough we have in the Expo RAM. 16-bit is just mad. I don't even... we have like, how many instructions do we have? We have a single ALU with 4, maybe 5 instructions. Let's see, and it's all handmade. 3. 3, I forgot there was 3 There's only 3 instructions. 16-bit could do like thousands of instructions. Wait, maybe it wouldn't have that many. Maybe. I actually don't know. I think that's each message, each thing has that much. So yeah, I'll need like mem copy, weird stuff. Yeah, I'll have to have, well, that won't be in the ALU instructions. I'll have them different place for indexing the RAM. This is so weird. It's like an illusion. The illusion of choice. Wait, oh, new person, what are you doing? Or an 8-bit fee. Hello, what are you doing? Sorry, I'm building a 4-bit computer. Sorry, I need to check chat, because I should have it like on my screen, but it's not on my screen. Wait, then what the hell's this? Why are there so many more? No. I forgot to connect the last, like, oh, there's so many more. What the hell? How did I forget about this? There's so much to do, man. I need, like, collaboration. The one CPU. I do like how it all layers up. Because, like, this thing, we have multiple of these. And it all packages up. 7, 8, 9. 9B. 10A. Oh, 10A maths. 10B. 11A. 11B. 12A. Yeah, 4-bit CPU. 12. Oh, computer. Oh, not C. 12B. 13A. Oh, shit. 13B. Oh, no, we've done something wrong. 14A. 14B. Oh, something's amiss. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What? Then what? Does 16 coming out of... You're kidding me, right? I didn't... One, two, three, 4, 6, 7, 8, 9, 10, 11, 15. Oh, yo. No, it's not even a big deal. What we do is we just shift it there. I thought I could. Because you can shift things around. I've done it that way. Oh, there's so many more. Man, this is a real headache. Ooh. A 15B. Okay, now we just gotta set up the allows, and this will need to move back as well. That looks like it's on an angle, but it's not. all the way there. Hmm. I had them going here, but then it's moved. Oh man. Surely I don't need all of these right now. Well, I really don't, but no, I do. For the RAM. Because easily will use up this. Well, I don't even have any way of indexing the RAM at this point. So, like no way of, I need a CPU that will be able to use the ALU. Make a 32-bit one, bro. Not make 32-bit to hard. It's too difficult. Yes. 16-bit, 8-bit, the Commodore 64 was 8-bit. Oh, hello. I'm making a 4-bit CPU. Yes, here's the schematics. This is a switch, I think. I've lost track. It is a switch. Similar to a multiplexer. Part of a multiplexer. It doesn't do much. Damn. So wait here. So let's have a look. Let's go to the ALU again. Oh, since I added stuff, it made it weird. Okay, never mind. It's not a problem. It got massive, even bigger. It's absurdly large already. Okay, so this ALU, we have certain. Man, I've explained this so many times. I'm just gonna go back to the. That's so cool. Oh my god, if I was editing the wrong one, I would have just. I wasn't, but. I would have just thrown it at the wall at that point. Oh no, because it was working. I would have just had to swap stuff out and it would have been stuff around. But this whole thing is. Man, I need to sleep. It's 11 o'clock. It's 11:10. Alright guys, we've done a lot of progress today. We've got an ALU, we've got RAM, we just, I guess, next couple days, oh shit, calm down. Next couple streams, we'll be turning this from what the heck it is now. We'll be linking up the RAM and the ALU in the CPU. Yeah, I need a bunch more of these. Maybe. Yeah. We'll do it with this RAM and yeah. We'll be able to store numbers, add in inputs, outputs, keyboard, all of that. Check the RAM. What about logism? Oh yeah, logism. I'll have to reboot everything. It's gonna take, well, it might not take as long because it's probably better. Maybe I can export things, make a script that converts it to something. Check Discord. Okay, see you guys. It was great.